Hi, everybody. We're doing today 2.4. So let's just jump right to it. Let's take a look at it. Hope you're having a good day. I'm having a great day out here in Hogwarts. It's always fun and sunny. So the sum of the indicators of the divisors of a number. So there's two things here. Basically, there's a lemma and there's a theorem. So now, what's a lemma? A lemma is a theorem and a theorem is a theorem. So what's the difference between a lemma and a theorem? A lemma is just a theorem which is useful in proving another theorem. So calling something a lemma is just really a subjective term. They're all theorems. So you want to usually a lot of times if you have a big theorem and then from that big theorem we can prove some others like offshoot of that. We'll call that offshoot a corollary. Here, there's like it's sort of like a but they're just theorems. Calling it a lemma, calling it a corollary, calling it a theorem, they're all just theorems. Anyway, if D is any divisor of M, so M is our original number, and D is any divisor, meaning that M is equal to some number N times D. Because if it's divisor, then it means I multiply D by some number N and I get my original number. So the number of integers not greater than M, right, mean less than or equal to M, which have with M the greatest common divisor D is phi of N. Now why is that? It's because every integer that's not greater than M having the divisor D is contained in the set D, 2D, 3D, ND. Now, these are all the multiples of D until you actually hit M itself, because ND is equal to M itself. Remember, that was the whole definition here. Now, the number of these integers which have with M the greatest common divisor D is the same as the number of integers in the set 1, 2, 3, up to N, which are relatively prime to M over D. And you see that from the way this is laid out. Or N, and for alpha D, which are which are prime to. So it's the numbers 1 through N, which are prime to N, and N is the same thing as M over D, because that's how it was defined again. So if you have alpha D, a multiple of D, and N, so alpha for any particular alpha D and N have or have not the greatest common divisor D according as alpha is or is not prime to M over D N. That actually made sense. So hence the number in question is phi of N. That's basically what we're saying here. So all the numbers that are relatively prime to N, that's how many we got over here. Now from the lemma, we could now prove this amazing theorem. If I would take all the divisors of a number and lay them all out, D1, D2, up to DR, R is whatever the biggest one, or it doesn't have to be biggest, that's just the order I'm doing it in. R is just some random number. Then if I take the phis of all these divisors, I wind up getting the original number M. So phi of D1 plus phi of D2 plus plus phi of DR is equal to M. And that is really amazing. That really, really, really is amazing. Now we're going to define integers M1, M2, MR by the relation. If I take M and divide it by D1, this could be M1. And if I divide it by D2, if I divide M by D2, I'm going to get M2, and so on and so forth. So the set of M positive integers not greater than M, and class. So we want to consider this set, and we want to classify them into R classes. So we're going to place the first class of those integers of the set, which have with M the greatest common divisor, M1. Their number is phi of D1, as you could see from the lemma. That's what we showed the lemma. Now place it in the second class the integers of the set which have with M the greatest common divisor, M2. Well, their number is going to be phi of D2. And if you keep on continuing this way till you get to the end, till you get to DR, we finally place the last class, the ones that have the greatest common divisor with them is MR, and their number is phi of DR, and every integer in the set falls into one and into just one of the R classes, and hence the total number m of integers in the set phi of d1, phi of dr, is going to the total is going to be m, and from this the theorem will immediately follow. And I want to show you just an example of how this, just an example of figuring this out. Let's say I take my number n is my big number. I should say m actually. My big number is 24. M equals 24. So here's the divisors of 24. You have 24, 12, 8, 6, 4, 3, 2, 1. These are all the different divisors. Now, phi of 24 is 8. You can figure that out. Phi of 12 is 4. Phi of 8 is 4. Phi of 6 is 2. Phi of 4 is 2. Phi of 3 is 2. Phi of 2 is 1. And phi of 1 is defined as 1. Well, if you add up all the numbers in this column, you see I did sum from B2 to B9, you get 24, which is the original number. And that's what our theorem is saying. That if you add these all up, you get the original number. Now let's say we start with the number 36. 36 is our M. So the divisors of 36 is 36, 18, 12, 9, 6, 4, 3, 2, 1. And phi of 36 is 12. You can work it out. Phi of 18 is 6. Phi of 12 is 4. If you add this column here, if you add the E column over there, you get 36. See, this is the sum from E2 to E10. I'm adding up all these numbers here. I want to be getting the original number 36. And that's really remarkable. And that's amazing. And that's what our theorem is telling us. So yay. Oops, that's not what I wanted. So what I want to say here, if you notice, phi of 1 is 1, phi of 2 is 1. Phi of 1 is 1, phi of 2 is 1. Other than that, all of these phis are even. So these are all even numbers here. And indeed, the first homework question asks us to prove that it's always going to be even. And that's actually kind of easy to do, really. Why? Because, let's go to a Google Doc here. First, let me show you what I'm talking about. This is problem number 1. Show that the indicator of any integer greater than 2 is even. There's probably various ways you could do this, but just one simple thing. Let's just go to our Google Doc and put this in there. Where is it? Okay. So going to our Google Doc here. So let's say you have phi. Oops. I want to do insert phi. Insert. Which one is phi? Is that it? That's row. Do a nice phi. PHI. Oh, okay, let's do that. Internal sensitive bulb, like small phi. Let's do that one. Yeah, like I say, I'm always used to doing. So this one's a nice one. All right. So phi of p is a prime, is going to be equal to p minus 1. Well, you all know that every prime is, and not only that, phi of, oops, that's not what I wanted. But we know that phi of p to the a is going to be, we already learned that that's going to be p of a, p to the a minus p to the a minus 1. We learned this already. Of course, we factored out a p of a, and we got a formula from that. But my point is that as long as we're talking about, as long as phi, as long as p is greater than 2, then P is odd, and P minus 1 is even, which means these are all even numbers here. P minus 1 is even, P to the A minus P to the A minus 1, these are all, this is the difference of two odd numbers. These are all even numbers. So we know that, you know, so basically phi of, so we know that if, like we said before, if M equals P, you know, to the, I'm just going to use A, B, and, you know, P to the A row here, and Q to the B. Oh, Q to the B, like QB. And then times, I don't know, R to the C. So you know that phi of M phi of M, should be a small m, by the way. Phi of M is equal to, let me just put the right letters in. That's Q, B, it's R to the, oops, to the C. Yeah, which is but wait a second. What if in this big letter M, what if P is happens equal to? Suppose M, let's say M, original number M. Let's say original number M is equal to, let's say our first number is 2 to the A. Well, whoops. Well, that's going to be, that's going to be equal to, 2 to the A. So this is going to be equal to 2 to the A. But again, this is the difference of, this is even. If A equals 1, then phi A equals 1, then phi of A just equals 1. So so we're covered. So if M has no odd factors, then I have a bunch of a product of even stuff. If there's all odd primes, if there's an even prime too, if A is greater than, I should say like this, I'm sorry, not greater than 1. So so if M is equal to 2 to the A times all these guys here, that's going to be 2 to the A. That's going to be this times an even number, the same even number that we got up here, and you know, and that's good, and that's even. Okay, fine. And if A happens to equal 1, it means I just have a factor of 2 and nothing else, and that's it. Then phi of P to the A, that just equals that's just going to equal just make it explicit. That's just going to be phi of 2, and that equals 1. And there we go. And that really, that's, so this is, let me just make a note here. This is 2.4. 2.4 exercise number 1. Alrighty. So that, my friend, is the story. I hope you enjoyed it as much as I did. And we'll see you guys next time. Bye. Bye, everybody.